All right, let's jump right into this explainer. Today we're unpacking the really fascinating physics behind why some materials conduct electricity perfectly, why others stubbornly block it, and why some, well, they just sit right in the middle waiting for the perfect conditions. We are talking about the physics of semiconductors. Here's our roadmap for today. We'll hit 6 key areas: classifying materials by resistivity, the limits of resistivity, the free electron theories, why early theories failed, the band theory solution, and finally, understanding EK diagrams. Let's get to it.
Starting off with Part 1, classifying materials by resistivity.
So let's kick off our macro to micro journey with something totally tangible, something we can easily measure right in a lab: resistivity. Basically, it just measures how strongly a material opposes the flow of electric current. And when we test this out in the real world, we get 3 very distinct physical categories. First up, highly conductive materials. Think the copper wiring inside your walls. Then we have perfectly insulating materials, like the glass in your windows. And finally, sitting right there in the sweet spot, we have the silicon semiconductors that literally power our entire digital world. Now, looking at the actual measurements, the sheer scale of difference here is pretty breathtaking. Conductors like copper and silver, they have a tiny, and I mean literally tiny, resistivity, somewhere around 10 to the negative 8th ohm meters. Insulators, on the flip side, massively exceed 10 to the 6th, sometimes even hitting 10 to the 16th ohm meters. It's a massive gap. And that huge gap leaves our specialized semiconductors, materials like silicon and germanium, sitting perfectly in the middle, generally ranging from 10 to the negative 3rd up to 10 to the 3rd ohm meters. Moving on to Section 2, the limits of resistivity. While this macroscopic way of classifying things is incredibly useful for basic engineering, it actually hides a massive scientific mystery underneath it all. Before we reveal the missing pieces of this physics puzzle, I want to test your own understanding real quick. Based on those broad categories we just established, which of these everyday materials strongly opposes electric current the most? Is it A, copper, B, glass, C, silicon, or D, all of the above? If you guessed B, glass, you hit the nail on the head. But here's the catch. Knowing that glass resists current doesn't tell us the whole story. You see, resistivity alone miserably fails to explain why a semiconductor's conductivity actually changes when you heat it up. It also totally fails to explain how charge carriers, specifically electrons and holes, are dynamically generated inside the material, or how they exhibit quantum behavior. A simple ohm meter reading just cannot explain the why.
Which brings us to Section 3, the free electron theories.
To solve these glaring limitations, early physicists realized they had to completely rethink things. They had to zoom all the way out of our macroscopic world and dive straight into the atomic level. Let's look at the timeline to see how this built up. Back in 1900, Paul Drude, whose work was later extended by Lorentz in 1909, proposed the classical free electron theory. They basically treated valence electrons like randomly bouncing balls moving through a constant potential, obeying classical mechanics and Maxwell-Boltzmann distributions. This meant multiple electrons could theoretically possess the exact same energy state. But as science evolved, we get to 1928. Sommerfeld introduces the quantum free electron theory. This was a real game changer because it brought in Pauli's exclusion principle, strictly stating that no more than 2 electrons could occupy the exact same orbital. Part 4. Why early theories failed. But, wow, even these brilliant scientific minds hit a major wall when their carefully crafted electron theories were put to the test. It must have been incredibly frustrating for physicists at the time. I mean, the classical model could successfully explain Ohm's law, sure, but it couldn't explain how conductivity depended on the actual number of electrons. It also couldn't explain how temperature, light, or impurities drastically altered a semiconductor's behavior. So, the quantum model stepped in to fix some of this. But, astonishingly, Sommerfeld's model completely failed to explain the fundamental difference between an insulator, a conductor, and a semiconductor at 0 Kelvin. Because it assumed conduction electrons occupied different discrete energy levels even at absolute zero, the math just blurred the lines between the material types entirely.
That brings us to Section 5, the band theory solution.
That dramatic failure of early models, it created an absolute necessity for a totally new theoretical framework, and that is band theory. Now, band theory works kind of like a crowded room. Imagine a single atom with its neat, distinct energy levels. Simple, right? But now, in a solid crystal, you have millions of these atoms crowded together in a repeating, periodic arrangement. As they get intimately close to each other, their outer valence orbitals heavily overlap, And because of Pauli's exclusion principle, all these electrons absolutely cannot share the same exact quantum state. So to give every single electron its own unique spot, those single atomic energy levels are forced to rapidly split into millions of closely spaced levels. They form these thick bands of allowed energies.
And what we're looking at here brilliantly illustrates that exact shift. We're moving from our basic macroscopic resistivity blocks to the true microscopic band structure. We aren't just looking at a simple block of silicon anymore. We are visualizing these specific conduction bands where electrons are free to move, the valence bands where they're normally bound tight, and, this is absolutely key, the crucial forbidden band gap sitting right between them. This gap is the secret sauce. It completely dictates whether an electron can actually jump across to become a free charge carrier or not.
Section 6. Understanding EK diagrams.
Okay, so knowing that bands exist is great, but solid-state physicists needed to meticulously map out exactly where these electron bands can physically exist inside the crystal. So they developed the EK diagram. Notice the wave vector formula for K here. When we treat the electron not just as a bouncing ball, but as a literal wave moving through the perfectly repeating structure of a crystal lattice, we find that the total energy E of that electron behaves very uniquely. These formulas conclusively prove that the energy of an electron is an even periodic function. It just repeats constantly, over and over, as the electron wave propagates through the uniform grid of the crystal.
And it's this periodic repetition that allows us to graph the energy and map out what physicists call Brillouin zones. This model perfectly outlines the boundaries of the first zone, showing it existing exactly between negative pi over a and positive pi over a. Crucially, it pinpoints the exact discontinuities, these really sharp breaks in the allowable energy states, and they occur precisely at k equals plus or minus n times pi over a. These discontinuities aren't just math. They represent very real physical restrictions where a semiconductor crystal simply forbids an electron from occupying that specific energy state. That, my friends, is the band gap, mathematically proven by the physics.
So we've journeyed from simply measuring how much a piece of wire resists electricity all the way down to proving exactly where an electron wave is permitted to exist inside a crystal lattice. Pretty wild, right? But as we continue to push silicon chips to their absolute microscopic limits, making them smaller and denser every single year, it really leaves us wondering. As our devices approach the very size of these atomic boundaries, what new quantum mysteries will the next generation of solid-state materials need to shatter? Keep exploring, keep questioning, and I'll catch you in the next explainer.